Okay, this is the second part of this video walkthrough of the January 2024 exam for Physics International A-Level Edexcel on Unit 5. So this was taken in the most recent modules, taken in January. My students have done it as a mock in April, and I'm now releasing my answers so students can make improvements. If you haven't done this paper, I would check with your teacher whether they want you to look at it. They may be holding it for a mock exam as well. Okay, so once again, make sure you've subscribed, like and share the video if you find it useful so we can increase our coverage. As I told you, we now have 160 subscribers, and it's a service I started offering in January, and obviously to make it worthwhile I need to get enough followers. Thank you very much. It'll be much appreciated. Okay, so the next question is question 17. Skylab was an early space station that orbited the Earth. Skylab contained a body mass measurement device. The device was a chair connected to a stiff spring. Okay, so we're basically using spring knowledge, so that'll be Hooke's law, things like that. So you're just thinking ahead. So when I'm underlining, this active reading is a good way of taking in the information properly rather than reading passively. Astronauts in orbit are sometimes described as weightless, okay, although they do experience a weight force. So they're not really weightless, they're just described as weightless. And I didn't realize that my students, when the first two I marked, they hadn't understood this concept of weightlessness. So I normally explain it when I do GCSE work. So this is the answer. Explain why astronauts may be described as weightless. In effect, astronauts and the space station that they're in are in free fall as they orbit the Earth. Okay, it's like they're continuously falling. The only difference is falling is straight down, and they're falling sideways around the Earth. So if this is the Earth, they're falling, but they're falling in at just the right velocity, where they're also got sideways constant speed. Yeah. So they're constantly in a state of falling. Now, if you were falling out of a plane, you wouldn't feel your weight. You wouldn't feel your weight in that when you measure your weight, you're standing on a spring balance, for example. The weighing machine in your bathroom scales has a spring in it. You wouldn't feel anything. So if you strapped your bathroom scales to your feet while you fell out of a plane, you would read 0 in terms of your weight. And objects in free fall feel weightless because they experience no contact force. So if you and your weighing scales are falling at the same rate, it's like you have no contact force. So actually feeling weight is normally due to the fact that something is you're making contact with something. That's why you feel weight when you're sitting on a chair or you're standing on your feet. So this is an important clarification of people who didn't understand what weightlessness meant. So I think students were saying that's because it's far away, so the gravity is weak. Well, you could work it out. You could work out the gravity based on this equation, gm over r squared, yeah, and work out how far away they are. You'll find that gravity is not 0, therefore they wouldn't be weightless. Okay. The spring was tested without oscillating. In other words, they just stretched it with a force of 175 newtons applied to the spring. So now, as I said before, you're going to ask about Hooke's law, F equals kx. The spring deformed by 28.9 centimeters. That means 0.289 meters. So keep doing this when you're reading the question to make sure you don't make any errors with units. When no one was sitting in a chair, so we can work out here the what? They're giving us F, we can work out K, can't we? So by knowing this, we can work out K. Just thinking ahead. When no one was sitting in the chair oscillated with a period of 0.858 seconds. So we know T, and we know the equation for T is 2 pi root m over K. Very similar in form to the period of the pendulum. Instead of length and gravity, you've got mass and K. Yeah? Well, K is the equivalent of a force, isn't it? Or kind of. All right, so when one of the astronauts sat in the chair oscillated with a period of t equal 2.26 seconds. Okay, so when no one was sitting, it was a period less than 1 second. Where someone was sitting, the mass is increased, so the period is increased because mass is directly proportional to the period. So the bigger the mass, the bigger the period. So you've got to calculate the mass of the astronaut. In other words, we've got to use this equation to find it out. But first, we need to find out k, and we find out k using Hooke's law. So k will be 175 divided by 0.289. Remember, you've got it in meters, so that's k. Once we know k, we know k, we know t, we know 2 pi. The only thing we don't know is m. So to find m, we just change the subject of the formula, get rid of the square root sign, so it will come out to kt squared over 4 pi squared. K is what we just worked out, so you put the k in, you put the period in, and this is the mass of the chair on its own. Okay, so once you do that, you work out the mass on the chair on its own is 11.3 kilograms. Okay, so you divide by 4 pi squared, you'll come to 11.3 kilograms. That's the mass of the chair. Okay, so when the man is sitting on it, it's going to be his mass, or the mass that you're working out is a combined mass. Okay, so when you do the same again, but this time you put the period of 2.26 seconds in it. This doesn't change, 4 pi squared doesn't change. The total mass that's causing that oscillation would be 70. Oh, apologize once again. I have to go through that again, so hopefully you followed me before. So when we work out the mass of the chair, we're just putting in the value for the period when the chair was empty. We'll come up with the mass from this equation of 11.3 kilograms. Now you put the astronaut in it, and that means the astronaut and the chair are oscillating it. So this is the total mass. It's the astronaut plus the chair. So it's exactly the same equation. You put the new period in, and you'll get the new mass. This is the total mass of the astronaut plus the chair. Take away 11.3, you're left with 67 kilograms to work out the mass of the astronaut. Okay? Subtract the mass of the chair, 11.3 off 78.3, you get 67.0 kilograms. And I've put it down to 3 significant figures. So I've put 67.0 because both of them are 3 significant figures. Here we've got 3 significant figures. Here we've got 3 significant figures. And all the data here is 3 significant figures that you're given. Okay? 175 newtons. So your answer should be to 3 significant figures. That's question 17. Question 18 is a 2-page question. So this is when they start getting longer. Kruger is a binary star system close to the Sun. The wavelength maximum of at which the intensity of radiation is maximum. Remember, that's Wien's law again. Is given as 850 nanometers. Yeah, so that's 850 times 10 to the minus 9 meters. Yeah. And for Kruger B, it's 1500 nanometers. So that's 1500 times 10 to the minus 9 meters. Okay, the website states that the surface temperature of Kruger A is double the surface temperature of Kruger B, so we can put this in there. Obviously, it'll be in Kelvin. So using Wien's law again, the temperature is proportional to whatever the constant is, gives you in the formula sheet. The temperature of A must be equal to the K, whatever the constant is. It's given to you in the equation, but we can cancel them out, so we don't actually need to know it. It's proportional, inverse proportional to the maximum wavelength. So for A, you just put constant divided by the wavelength, and do the same for B. So if you want to then work out that it's double, so if we put in K over lambda, basically only the lambdas are going to change. The K's cancel out, so you'll see here the K's cancel out by doing the TA over 2TB. So we want it to be, TA should be double, it comes to 1.76, so it's less than 2. So when you put in the values of the ratio of the maximum wavelengths, then you get a ratio of 1.76, so it's not 2, so it's not quite twice that of Kruger B. Okay. Now, remember earlier in the multiple choice question they talked about stellar parallax. Okay, so now they're talking about what's called the standard candle. Okay. Just waiting for the video to self-focus. Seems to be a bit fuzzy. I don't know why it's gone so fuzzy. Anyway, hopefully you can still see it. Let's try to zoom out, zoom in. It looks a bit fuzzy, doesn't it? Anyway, I'm going to have to continue. So Kruger B can be used as a standard candle, it says. Yeah. Just going to see if I can do anything. Autofocus, there it is. There's a button called autofocus. That's strange. So I might stop this video and start again to see what happens. We're going to finish this question anyway. So standard candles, it says Kruger B can be used as standard candles. So standard candles are stars with known luminosities. Okay. So describe how standard candles can be used to determine distances to galaxies. So if you can locate such a star in the galaxy being observed, yeah, and measure its intensity, observed from Earth, obviously, yeah. The intensity is I, we talked about it in an earlier question, using the equation I equals L over 4 pi d squared, which is the distance to the star, to determine the distance, yeah, to the galaxy standard candle, where L is a known luminosity. So once you know the luminosity, yeah, and you can then measure intensity to a more distant one, yeah, then you can use this equation to work it out. So I'm going to have to stop this video and see what's happening with the focus of the camera, and then I'll continue in the next video. Apologies for that. So I'll show you this on the next video so you can actually see the writing more clearly. Okay, so join me in the third part of this video. Apologies for the technical errors, technical problem. Okay, thanks for now. Speak to you soon.